Hello geometry students. In this lesson in our 6.4, 6.5 notes, we're going to continue our discussion of parallelograms, and we will specifically be looking at parallelograms that are rectangles, rhombi, and squares. So let's start with our discussion of rectangles. So let's start with the definition. Definition of a rectangle. A parallelogram is a rectangle if and only if it has 4 right angles. All right, so not every parallelogram is a rectangle, only those that have 4 right angles. So also, because a rectangle is a parallelogram, that means that every property that a parallelogram has also applies to a rectangle. So not only does a rectangle have 4 right angles, but also its opposite sides are going to be both parallel because it's a parallelogram and congruent because that's a property of every parallelogram. Likewise, opposite angles are going to be congruent. Okay, consecutive angles will be supplementary because again, every rectangle is a parallelogram, so any property that applies to parallelograms would apply to rectangles. And last but not least, remember diagonals bisect each other. That is also true of every parallelogram. But in addition to these, the following theorems add another property about the diagonals of a rectangle. And this first theorem says that the diagonals of a rectangle are congruent. Okay, so make a note, please, that this property is not true of all parallelograms. Okay, so not every time you see a parallelogram, it's not going to be true that the diagonals are congruent. It's only going to be true if the parallelogram is a rectangle. So let's go ahead and state that diagram that theorem in terms of this diagram. Here we have JKLM is a rectangle. Okay, so what we conclude is if JKLM is a rectangle, we can conclude about its diagonals that its diagonals are congruent. That diagonal JL is going to be congruent to diagonal KM. Now let's take a look at a theorem that will be the converse of the theorem that we just stated. This theorem says that if the diagonals of a parallelogram are congruent, okay, then the parallelogram has to be a rectangle. Okay, so with that in mind, I want you to think about this question. So suppose that you're building a house and it's time to cut an opening in the wall of this house to install a rectangular door. Can you think of a way to guarantee that the opening you cut is in the shape of a rectangle? If you've ever been around anybody who builds things, they'll tell you that the rule that they follow is to measure twice and cut once. So in other words, before they cut out these dotted lines to create that rectangular space for the door, we want to make sure that it actually is a rectangle so that the rectangular door will fit in that space. So what could we do to guarantee that the opening that we cut is actually a rectangle? Well, we can use this theorem that says if the diagonals of a parallelogram are congruent, then that parallelogram has to be a rectangle. So what we could do is we could measure the diagonals of this rectangle, and if those diagonals are congruent, then we know that we are cutting out an actual rectangle. Okay, so what can we do? We can measure the diagonals. Okay, if the diagonals are congruent, then the opening we cut is a rectangle. Okay, and then let's go ahead and talk about another special parallelogram, and the special parallelogram we're going to talk about now is called a rhombus. So the definition says a parallelogram is a rhombus if and only if it has 4 congruent sides. Okay, so for example, we can take a look at this parallelogram. This parallelogram has 4 congruent sides, so we can call that a rhombus. All right, let's take a look at some theorems about the diagonals of a rhombus, and we're going to go ahead and prove those theorems. The first theorem says the following. It says that the theorems, that if a parallelogram is a rhombus, then its diagonals are perpendicular. All right, so the hypothesis of this theorem is that we have a parallelogram that's a rhombus. And so what we're going to prove is that its diagonals are perpendicular. So let's go ahead and write our given statement in terms of this diagram. So we are assuming that we have a parallelogram that's a rhombus. So we are going to assume that we have rhombus, we're going to call it rhombus ABCD. And so what we're going to prove is that the diagonals are perpendicular to each other. So we're going to prove that segment AC, one of the diagonals, is perpendicular to segment BD. Okay, so what that means is this diagram actually has a slight error in it. Since we're trying to prove that the diagonals are perpendicular, we shouldn't have marked this diagonal. We shouldn't have that right angle symbol there. So we're going to mark over that in just a second. Let's go ahead and label a couple of angles. Let's call this angle angle 1, and go ahead and write right on top of that right angle symbol, and let's call that angle 2. So what we have here, angles 1 and 2 are a linear pair of angles, and what we're going to prove is that we're going to prove that angle 1 is congruent to angle 2, because when we have a linear pair of congruent angles, we can conclude that those two angles form perpendicular lines. So to get angle 1 congruent to angle 2, the way we're going to do that is to get a couple of triangles congruent. So let's see if we can get this triangle that I'm going to shade blue. Let's see if we can get it congruent to this yellow triangle. Okay, so to do that, let's see if we can get the two triangles congruent by side, side, side. Remember, ABCD is a rhombus, so AB is going to be congruent to BC. The two triangles share a side that's congruent to itself, and also, since this rhombus is also a parallelogram, the diagonals bisect each other, so segment AE is going to be congruent to segment CE. So it's going to be pretty easy to get the two triangles congruent to each other. Therefore, angle 1 will be congruent to angle 2 by CPCTC, and when we have a linear pair of congruent angles, we can conclude that they form perpendicular lines. So let's get busy getting those two triangles congruent. So let's start with what we're given. First of all, we're given that we have rhombus ABCD. ABCD, all right, so that's given information, okay? So since we have a rhombus, then we can go ahead and say in step 2 that side AB is congruent to side BC. Let me go ahead and mark those. AB congruent to BC, and what justifies that is definition of a rhombus. Remember, a rhombus is a parallelogram that has all sides congruent. All right, so there's one pair of sides, and then as we mentioned earlier, remember the two triangles share a side. We can say that this side BE is congruent to itself. So we're going to say that segment BE is congruent to segment BE, and that is the reflexive property of congruence. So that's a second pair of sides congruent. And then lastly, remember this is a parallelogram, and the diagonals of a parallelogram bisect each other. So this segment AC is being bisected. So segment AE is congruent to segment CE. So that's going to be our third pair of sides congruent. So we're going to say in step 4 that segment AE is congruent to segment CE, because if we have a parallelogram, then diagonals bisect each other. All right. And so now we have enough to guarantee that the two triangles are congruent. In steps 2, 3, and 4, we showed that we have 3 pairs of sides congruent. So I'm going to call the blue triangle, I'm going to call it triangle ABE. And so then we would say that triangle ABE is congruent to triangle CBE. So the corresponding parts match up, okay? And our reason is because we found 3 pairs of congruent sides three pairs of corresponding sides congruent. So side, side, side implies congruent triangles, all right? And so now in step 6, now that the two triangles are congruent, we can say that angle 1 is congruent to angle 2 by CPCTC. And once we have angles 1 and 2 congruent to each other, remember 1 and 2 also form a linear pair. And anytime we have a linear pair of congruent angles, we know we have perpendicular lines. So in step 7 then, we can say that segment AC is perpendicular to segment BD, okay? And the reason is a theorem we haven't seen it in a while, but it says when we have a linear pair of congruent angles, that implies that we have perpendicular lines. All right, so we have now proved then that anytime we have a parallelogram that's a rhombus, we know that its diagonals are going to be perpendicular to each other. So let's take a look at the second proof. What we're going to prove here is if we have a parallelogram that's a rhombus, we're going to prove that each diagonal bisects a pair of opposite angles, okay? So for example, what we're going to prove is that this diagonal NQ bisects all of this angle. So 5 is congruent to 6 and 7 is congruent to 8. And this segment PR bisects this angle and this angle. So 1 is congruent to 2 and 3 is congruent to 4. All right, so let's assume our hypothesis that we have a parallelogram that's a rhombus. And then what we're going to prove is that each diagonal bisects a pair of opposite angles. So what we're going to do in this proof is that we're going to prove that angles 1 and 2 are congruent and 3 and 4 are congruent. So we will prove the theorem for diagonal PR, and then we'll assume that a similar proof could be written for diagonal NQ. All right, so our hypothesis then, what we're given, what we're going to assume to be true, is that we have a rhombus by the name of NPQR. And what we're going to prove is that angle 1 is congruent to angle 2, and we're going to prove that angle 3 is congruent to angle 4. In other words, what we're proving is that this angle PR is bisecting a pair of opposite angles. All right, so let's start with our given. Let's start with the fact that we have rhombus NPQR. Okay, that's given. Okay, so now to get 1 and 2 congruent and 3 and 4 congruent, we're going to need to get a couple of triangles congruent. So let me highlight the triangles that we want to get congruent. Let's see if we can get this triangle. I'm going to highlight it blue. Okay. Let's get it congruent to this triangle that I'm going to shade yellow. All right, so getting those triangles congruent is going to be pretty simple. Remember, this is a rhombus, so that means we have 4 congruent sides. So for example, let's see, NP is going to be congruent to PQ, and also NR is congruent to RQ. Okay, so we already have 2 pairs of congruent sides, and then also the triangles share a side that's congruent to itself. So we're going to be able to get this blue triangle congruent to this yellow triangle by side, side, side. All right, so let's go ahead and talk about those sides of the rhombus that are congruent. So let's go ahead and write down that segment NP is congruent to segment PQ, and also that segment RN is congruent to segment RQ. So I've marked those on the diagram. We have NP congruent to PQ, and we have RN congruent to RQ. Okay, now the reason why that is true is because we assume that NPR is a rhombus, so we can justify step 2 with the definition of a rhombus. If I can squeeze that in there. Okay, so there's 2 pairs of congruent sides, and then remember we said that the blue triangle and the yellow triangle share a side. I guess we can call it PR. Side PR is congruent to itself, all right, and we'll justify that with the reflexive property of congruence, okay. So now we have enough to get the 2 triangles congruent. So I'm going to call the blue triangle, I'm going to call it triangle RNP. And so we're going to say that triangle RNP is going to be congruent to triangle RQP so that we get corresponding parts to match up. So we'll try it RQP, okay? And our reason is side, side, side implies congruent triangles. Okay, so now you'll see that R in the blue triangle corresponds to R in the yellow triangle, and also angle P in the blue triangle corresponds to angle P in the yellow. In other words, if we use our angle numbers, we can say in step 5 that angle 1 is congruent to angle 2, and then angle 3 is congruent to angle 4, and our reason is because they are corresponding parts of congruent triangles, and corresponding parts of congruent triangles are congruent. All right, so what we have proven then is that this angle, or excuse me, this diagonal PR bisects a pair of opposite angles. So you could see that we could write a similar proof to prove that angle 5 is congruent to angle 6 and angle 7 is congruent to angle 8. In other words, that NQ also bisects that. So, well, let's just make a note that the proof of angle 5 being congruent to angle 6 and angle 7 being congruent to angle 8 is similar. We're not going to take time to write that proof, but it would be very similar to the proof that we just did. So in other words, we basically proved that anytime we have a parallelogram that's a rhombus, each diagonal bisects a pair of opposite angles. Okay, so let's see if we can use what we have learned about rhombi. Rhombi is plural of rhombus, by the way, to solve a couple of problems. So in this example, we're told that the diagonals of rhombus FGHJ intersect at K. Use the given information to find each measure or value. So let's start with letter A that says, if the measure of angle FJH, so if this whole angle, if that whole red angle measures 82 degrees, we're being asked to find the measure of angle KHJ. So we're going to find the measure of this angle. Okay, so to do that, what I want to do is I'm going to highlight a triangle. Let's just take a look at this triangle right here. Well, we know something about this triangle. We know that this triangle is a right triangle. The reason why, whoops, let me get a pen. The reason why we know that this is a right triangle is because we just proved a minute ago that the diagonals of a rhombus are always perpendicular. So that makes this yellow triangle a right triangle, which means I'm going to number a couple of angles. I'm going to number this angle 1 and this angle 2. Angles 1 and 2 are going to be complementary. Remember, the acute angles of a right angle are complementary. Angle 1, we know that angle 1 is going to be 41 degrees. So let me see if I can draw a little angle. So angle 1 is 41 degrees. Remember, we just proved a minute ago that the diagonals of a rhombus bisect opposite angles. So if this whole red arc is 82 degrees, that means angle 1 is 41 degrees. And so angle 2 then, which is angle KHJ, which we're being asked to find, is the complement of this 41 degree angle. So that means that the measure of angle let me write that so it's legible. Sorry about that. The measure of angle KHJ then is equal to 41 degrees. All right. And then letter B says, if GH is x plus 9, so let's go ahead and label that. So if this measure is x plus 9, and we're told that JH is 5x minus 2, that's this segment here. So it is 5x minus 2, then find x. Well, that's going to be pretty easy because we're told that this is a rhombus, and since it's a rhombus, that means that all sides are congruent to each other. So I can put a tick mark here and a tick mark here. So if these two segments are congruent, that means their measures are equal, and I can take x plus 9 and 5x minus 2 and set them equal to each other. So x plus 9 is going to be equal to 5x minus 2. So let's solve that. I'm going to go ahead and subtract x from both sides and add 2 to both sides. I hope I don't lose you if I do two things, and well, maybe I'll just do one thing at a time. Let's just go ahead and subtract an x from both sides. So we would have 9 is equal to 4x minus 2, and then add 2 to both sides, so we get 11 is equal to 4x. And then last but not least, let's divide both sides by 4, so x turns out to be 11/4. All right, so that brings us to our last special parallelogram, and that last special parallelogram is a square. So what is a square? Let's look at a definition. A parallelogram is a square if and only if it has four congruent sides, and it has 4 right angles. Another way we could say this is that a parallelogram is a square if and only if it is a rhombus and a rectangle at the same time. So what I'd like to do here is use this Venn diagram to kind of summarize all these special parallelograms that we've talked about in this lesson. So let's go ahead and label this outer rectangle-ish shape as the set of all parallelograms. So remember, what makes a parallelogram a parallelogram? The fact that it has 2 pairs of parallel sides. Okay, now in that set of parallelograms, we have some special parallelograms. First, we talked about rectangles. So let's let this oval represent the set of all rectangles. And remember what the definition of a rectangle. A parallelogram is a rectangle if and only if it has 4 right angles. Okay? And then the next special parallelogram we talked about was a rhombus. Let's let this oval represent the set of all rhombi. Okay? So I guess we'll write plural. We'll write rhombi. Okay, so what makes a rhombus a rhombus? The fact that it has 4 congruent sides. Okay, so then if we look at the intersection of those two sets, the set of rectangles and the set of rhombi, in other words, the shapes that are both a rectangle and a rhombus at the same time, that would be the set of squares. Okay, so squares then are a very special parallelogram. Every property that applies to a parallelogram will apply to a square. Every property that applies to a rectangle will apply to a square. So for example, the diagonals of a rectangle are congruent. The diagonals of a square would be congruent. Every property that applies to a rhombus will apply to a square. So for example, its diagonals are perpendicular, so therefore the diagonals of a square will be perpendicular. Okay, and so the last thing we're going to do in this lesson is we're going to look at the flip side. Let's look at some conditions that guarantee when a quadrilateral is a rhombus or a square. We've been looking at rhombi and we've been looking at squares, and we've been talking about the properties of those. So now let's look at the other side of the coin. What conditions would guarantee that a quadrilateral is a rhombus or a square? Well, the first condition we're going to look at is anytime we have a parallelogram with perpendicular diagonals, we can conclude that that parallelogram is a rhombus. Oops, I got to spell that right. Is a rhombus, okay? So let's go ahead and write this in terms of this diagram. So in other words, if you look at this diagram, we can see that diagonal KM is perpendicular to diagonal JL. So if KM is perpendicular to JL, then we can conclude that JKLM is a rhombus. Okay? And then number 2 says the following. If one diagonal of a parallelogram bisects a pair of opposite angles, then we can conclude that that parallelogram is a rhombus. Now, it doesn't have to be true of both diagonals, so let's just pick one diagonal. Let's pick diagonal WY, okay? And if that diagonal bisects a pair of opposite angles, we can assume that this parallelogram is a rhombus. So let's write that theorem in terms of this diagram. In other words, we can say that if angle 1 is congruent to angle 2 and angle 3 is congruent to angle 4, then we can conclude that WXYZ is a rhombus. Rhombus. All right? And then number 3, and condition, if we have a parallelogram with one pair of congruent consecutive sides, so one pair of congruent consecutive sides, that's enough to guarantee that that parallelogram is a rhombus. Okay, so we don't need to know anything about the other pair of consecutive sides, but if we know that we have a shape that's a quadrilateral that's a parallelogram, if there's one pair of consecutive congruent sides, that's enough to guarantee that that parallelogram is a rhombus. And then last but not, so let's write that theorem in terms of this diagram. So we would say that if segment AB is congruent to segment BC, in other words, if we have a pair of consecutive congruent sides, then we can conclude that ABCD is a rhombus. All right, and then last but not least, let's take a look at number 4. Number 4 says that if a quadrilateral is both a rectangle, we've kind of already mentioned this, but a rectangle and a rhombus, okay, if you look up at that Venn diagram, then that's enough to guarantee that that quadrilateral is a square. All right, so that takes care of our 6.4, 6.5 notes. If you have any questions, make sure that you ask me when I see you in class.